Now we're going to look at the small sample case. The mean exit velocity of all home runs hit in Major League Baseball is 103.53 miles per hour. So that's literally how fast the ball is traveling after it leaves the bat. Over his career, Mike Trout of the Los Angeles Angels has hit 240 home runs. The following data represent the exit velocity of a random sample of 10 home runs hit by Trout. Does the evidence suggest that Trout's home run exit velocity differs from the league? So here, our variable of interest is the exit velocity of the ball, which is a quantitative variable. We want to know if the home run exit velocity of Trout differs from that of the league. We know the mean exit velocity of all balls in the league is 103.53 miles per hour. So the statement of no change, no effect, no difference would be that there's no difference between the exit velocity of all home runs hit and the exit velocity of a Trout home run. And so our null hypothesis would be, what do you think?
353.
Yeah, our mean equals 103.53.
Yeah, exactly. The mean is 103.53 miles per hour. Make sure you always put the units of measure in there. And then again, in words, that means the exit velocity of a Trout home run is no different from the exit velocity or mean exit velocity of any home run. What are we looking for evidence to demonstrate?
Does it differ from the league?
Differ from the league. How would I write that?
Not equal to?
Yeah, there you go. Not equal to. So the alternative is that the mean is not equal to 103.53 miles per hour. The textbook step, the level of significance business, is that alpha is 0.05. I want to verify that I can use students' t-distribution to obtain a p-value. So I need a random sample or data from a randomized trial. This happens to be a random sample of 10 home runs, so I have that.
Mm-hmm.
Notice here, though, that my sample size is small, right? I only have 10 home runs.
Right.
Because my sample size is small, two things have to be satisfied. Thing one, the sample must come from a normal population. Thing two, I can't have any outliers.
Mm.
To check if the data come from a normal population, that's where we use a normal probability plot. To check if we have no outliers, that's where I use a box plot. So what I have to do is enter this data into StatCrunch and draw a normal probability plot and draw a box plot. So the variable is called exit velocity. I have 108.9, 104.7, 105.7, 106.8, and 103.9. So in StatCrunch, the normal probability plot is under graph, and it's called a QQ plot, a quantile plot. So we select that. There's the variable exit velocity. Add the correlation statistic, and I like the normal quantiles drawn on the vertical axis. And then we click compute. We're getting a correlation of 0.979. Recall that I've given you a table 6 that we use to compare this correlation stat to. That table 6 is in your MyLab course. So you go to the video and resource library, you go to learning tools, and then there's the formula table card. In your MyLab homework, this table that I'm about to show you will always be an option as a pop-up in the homework problem. So you don't have to go to this formula table card. But there's that table 6 that I was talking about. So notice the correlation stat, which is 0.979, is greater than the critical value for n equals 10, because we have 10 home runs. It's 0.918. So because 0.0979 is greater than 0.918, it is reasonable to conclude that exit velocity is approximately normal. The other thing that we want to check for is whether or not I have outliers. I check for outliers by drawing a box plot. So that's where we go graph, box plot of exit velocity. Check the box that says use fences to identify outliers, draw boxes horizontally, and title your graph. So this is Trout's exit velocity, we'll just say in miles per hour. And there we have it. No outliers are showing up. One other item that I want to mention to you is that we had told you that there's a second option rather than drawing that normal probability plot, namely that if the box plot is fairly symmetric, then we can use the robustness of this method using students' t-distribution and feel comfortable. This box plot is showing a pretty decent amount of symmetry in our data. The median is pretty much in the center, and while the right whisker is slightly longer than the left whisker, it's still showing decent symmetry. That's the second option that we gave you. The last thing to check besides that is your sample size no more than 5% of the population size? Here I'm telling you that Trout has hit 240 home runs. If you do 5% of 240, you get 12. So my sample size of 10 is less than 5% of the population size. So the independence requirement is satisfied. So now I can go ahead and use students' t-distribution. To do that, you select stat, t-stats, one sample. This time we're going to pick with data because I have raw data. There's my exit velocity. The mean stated in the null is 103.53. And the alternative is a not equal to alternative. Click compute, and we get our results. So the p-value is 0.0089. Agree?
Yes.
So here's how we would interpret that. If the mean exit velocity of a Trout home run is 103.53 miles per hour, we would expect to observe a mean exit velocity of 106.4 miles per hour or more extreme than that in about, 9 of every 1,000 repetitions of this study. The reason I say as extreme or more extreme than 106.4 miles per hour is because this is a two-tailed test. So in the two-tailed test, that's how you phrase it. You don't say 106.4 or higher because that would suggest we have a right-tailed test. So in the two-tailed test, always say as extreme or more extreme. So regardless, you observe something that you'd expect to observe about 9 times out of 1,000 if the statement in the null is true. So you certainly observe something that is highly unusual if the statement in the null is true. Because these results are so unusual, we would take that as evidence against the statement in the null. Or using the textbook rule, our p-value of 0.0089 is certainly less than the level of significance, and so we're going to reject. Right? 0.0089 is less than 0.05, so we reject. And so now we're ready to state our conclusion. There is sufficient evidence to conclude the mean exit velocity of a trout home run differs from the league, which differs from 103.53 miles per hour. And if you really wanted to gauge what the mean exit velocity of a trout home run is, you could use, again, a confidence interval, right? So I could literally go back here and go options, edit, and change this to a confidence interval. And now I'd be able to say, I'm 95% confident a trout home run has an exit velocity between 104.45 miles per hour and 108.35 miles per hour, which is clearly not including the league average. And so that again suggests a Mike Trout home run has an exit velocity that differs from the league in general.
So a good two ways to do it.
Yeah. Again, a lot of folks like using the confidence interval because it gives you that extra information.
I see why.
Yeah.